Okay, so let's continue with mechanical vibration. I will just do a quick recap. Can everybody see the slide presentation? Hello.
Yes, sir.
Okay. So I will just do a quick recap of the things we are supposed to do. So after completing this module, students should be able to understand the significance of history of vibration. So we have already done that. Define basic terms of mechanical vibration. Understand the applications of study of vibration. So we have got a sort of overview. Classify vibration based on various aspects of vibration. So we are on this step, and also we have to learn how to apply the vibration analysis process. Just a minute. All of you received today's notes.
Yes, sir.
Yes, sir.
Okay, so let's start with the let's do a quick recap. So we have discussed what is natural frequency, frequency at which the system tends to oscillate in the absence of any external force, and we also studied what is resonance. A natural frequency equal to force frequency, and the shape exhibited by the vibrating element at the various frequency is called as the mode shape. Okay, and we discussed what is a vibration or a simple oscillation by means of a simple pendulum. We identified the various basic elements of a vibrating system, which consists of a spring, damper, and a mass. Okay, generally these systems are referred as spring, mass, damper system. Okay, we have started with the classification, and we did the classification based on degree of freedom. That is the minimum number of independent coordinates required to determine completely the position of all parts of the system at any instance of time defines the degree of freedom system. And we identified single degree, 2 degree, and 3 degree, and we kept on if we keep on discretizing this system and we take this number of mass elements to infinity, we get a system. This system is called as a continuous system. All right, and example of that is this cantilever beam. So we have this continuous system with some infinite number of masses placed next to each other. All right, so we can define a term. This is m as mass per unit length. So total mass will be equal to the small m into the length of this bar. Right, so that will be the total. And we can so this system will have infinite degree of freedom, and it will vibrate about its mean position. Right. So this will be the mean equilibrium position, and it will vibrate about the mean equilibrium. We can convert this continuous system into a distributed system or a discrete system by assuming that the entire mass is concentrated at the end of the cantilever beam. So total mass is m and length is L, the same as the length of the beam, and this stiffness element or we can call it like a spring. You can find the properties like stiffness of the spring using the properties of the cross section, that is the Young's modulus, area of cross section, and mi of the beam. All right. So this is how we can convert a continuous system into a discrete system. Classification as per your course content, types of vibration. They are broadly classified into single degree and multi-degree of freedom system. Single degree of freedom system, that means this is types of vibration that you will be studying basically. So you have free and force in multi-degree also, but you will not be studying free and you will be studying only free vibration under multi-degree of freedom system. So in single degree of freedom system, you will be studying both free and force vibration. In free vibrations, you will be studying both damped and undamped. Okay. So when a system vibrates, what happens? And if it is damped, okay, if the system is damped, right, the amplitude of vibrations goes on decreasing. So damping is a property of the system that can be used to decrease the amplitude of vibration. Right? So damping is a property of a system that can be used to decrease the amplitude of vibration. All right. Then classification based on the direction of vibration. So in this the mean equilibrium position is defined, and this can be classified into longitudinal vibration. All right, where this is the mean equilibrium position, or transverse vibration, where again 2 is the mean equilibrium position, or torsional vibration, that is about the axis of the shaft. These are the basically types of vibration based on the direction. Okay? So question can be asked on any of these types. Classify the vibration based on like specific type, like based on direction or based on degree of freedom, etc. All right. Now let's go to this important topic, that is linear and non-linear vibration. That where the most of the quiz questions are based on this. So can somebody tell me what do you understand? What do you understand by linear and non-linear? So what we are doing in this subject is we are establishing a governing differential equation. Okay? So our aim is to establish a governing differential equation. Right? So in this example, I have shown this spring mass damper system. So a mass m is attached to a spring. This is the spring, and on the other side that is a damper. K is the spring constant, C is the damping coefficient, and m is the mass. And this mass is oscillating with acceleration x double dot. All right. So for this equation, when we are generally analyzing any system, then we establish a governing differential equation. Okay. So now our question comes: in which case we call the vibration of this mass a linear vibration, and when do we call the mass as a non-linear vibration? Can anybody think based on whatever information that is provided to you? So what will be the criteria to establish whether the vibration of this mass is a linear vibration or non-linear vibration? So we use this governing differential equation. If the governing differential equation is linear, that we obtained is linear, then the vibrations will be linear. And if the governing differential equation is non-linear, then the vibration also will be non-linear. Right? So if GDE stands for governing differential equation, the vibrations will be linear, If it is non-linear, then the vibration also will be non-linear. Now the question comes, what is a linear governing differential equation? All right. So suppose, can anybody tell me what is a linear governing differential equation? So a differential equation is linear if there is a variable y, and this variable y we can write in the form y, in the form a.
Sir, there is a x is linear and x square or any power of x is not linear, sir.
Not like that. It is not like that at all. Okay, so I will just write a equation. So if I write it in this format, see, y is a function of x basically. All right. And if I am able to write the governing differential equation in this format, that is ax dn by y dx raised to n. So that is the nth derivative, and there is a coefficient. This coefficient is placed in front of y and its derivatives. Okay, so let me write the equation completely. Plus a1x lecture plus a1x dy by dx. So as you can see, you should note down nth derivative, nth coefficient, and first derivative, first coefficient. It is like that basically. Okay. Plus a0 x into y is equal to g of x. Right? So you can write, so in front of y, and so in front of y, so this is y, and in front of derivatives of y. So these are the derivatives of y, 1 and up till n. Okay, so there are functions that are placed in front of y and derivatives of y. So these are those functions. Those functions should be pure functions of x. All right, pure functions of x. All right. So as you can see, all of these are pure functions of x. So this is a what you say, a linear governing differential equation, and y and its derivatives are all to the first power. Okay, the derivatives of y and the derivatives of y are to the first power. So I will write both these points. So for this governing differential equation, in front of y, so the governing differential equation, again I will write it just for clarity, that is a1x dx dny by dx raised to n plus a1x dy by dx plus a0 x into y is equal to g of x, where g is the function of x. Okay, so conditions must be satisfied. In front of y and its derivatives, there should be a pure function of x, correct? Which is there in our case in the equation which I have just showed, and y and its derivatives are all to the first power. What do you understand by first power? Can somebody tell me? Why?
Single power of x.
No, I am asking about, see, I'm talking about the second point. See, x can be anything. See, a1 of x can be either e of x, or it can be x square, or x cube, anything it can be. But these derivatives and y, they cannot be to this power. The power of that should be, this should be always raised to 1. Okay, dy by dx also should be raised to 1, and y should be also raised to 1. Alright, so that is what you mean by the first y and its derivatives are all of the first power. This power, this cannot be y square. Okay, this cannot be dy by dx square or dn by dx, dny by dx raised to n square or cube or anything like that. It should be first power. And these coefficients which are placed in front of y, okay, these are placed in front of y. All this and its derivatives, they should be pure function of x. So it can be anything, but there cannot be any other variable other than x in this coefficient. All right. So these two rules should be satisfied. So we'll see some examples, and then we'll come back to our problem. So just to get a good sense whether you have followed which is a linear, and if you are able to identify which is a linear and non-linear equation. Okay. So y double dash plus e raised to x y dash plus y is equal to sine of x. So is this a linear or non-linear?
Linear.
Linear.
Correct. Okay. Now, so this is first example. Second example, let's go. So this is y triple dash plus 3y into y double dash plus y e raised to x. What about this equation?
Non-linear.
Because coefficient of y double dash is not a function of x, is not a pure function of x. So this can be like 3y into x raised to 0. So it is not a pure function of x, there is a y term in it. So this is a non-linear equation. One more example we will do, and then we will shift to our current equation which we are going to do. So x square dy by dx plus y is equal to 7. How about this one?
Linear.
Linear. Okay. So we are now clear about what is a linear and what is a non-linear equation, because depending upon that, it is going to affect our analysis. Okay. If the equation is non-linear, then the solution which we derive will be completely different from what is a linear. Okay. All right. So now let's go to our example. All right. So this is a spring mass damper system. So so first thing I will do is I will draw a free body diagram for this. All of you are aware about free body diagram, I hope. I think most of you have done mechanics with me. One lecture I always dedicate to just the development of free body diagram. So this is a mass. It is moving with acceleration x double dot. X double dot stands for acceleration, and this is moving down. So opposing forces are generated in the spring and damper. Okay, so whatever is the direction of the motion, the spring and the damper will generate force in opposite direction. Okay, if it is moving down, obviously spring will develop a force kx, where x is the displacement. So this is our spring force. And damper, the role of the damper is to reduce the amplitude. Okay, so whatever direction it is moving, then again it has to be in opposite direction, and the damping force is given as Cx dot. Why it is coming as Cx dot, that detailed discussion we'll do later. So for now, you just take it for reference that it is the damping force, and the magnitude of that is Cx dot. C is the damping coefficient, and x dot is the velocity. Okay. So now let's write the various forces acting on it. So various forces acting on it are the inertia forces, and that is given as ma, that is mass into acceleration, or it can be written as mx double dot. Okay, and you have the opposing forces.
So
And that is,
could you
yes,
explain what x double dot is again?
x double dot is the second derivative of x. So x is the displacement, x dot is dx by dt, and x double dot is d square x by dt square. That is the second derivative of time. That is nothing but your acceleration.
Acceleration. Okay, sir.
Okay, this is your acceleration. Okay, so opposing forces will be the summation of spring forces plus the damping forces. All right, so this will be minus kx minus cx dot. Okay. And both have to be balanced. So all these equations, can you tell me what are the types? What are the type of these equations in terms of linear or non-linear?
Linear.
All are linear. So these all these equations are linear. All are linear equations. All right. So we'll derive the equation of the motion in just a minute. But now let's focus our discussion on the linearity and non-linearity of the system. Okay. So for a linear system, for a linear vibration, all the basic components of the vibrating system, that is the spring, mass, and the damper, they behave linearly. Okay. Well, how do you conclude it? We just derived the equation for that. If, however, any of these basic components behave non-linearly, then the vibration will be non-linear. Okay. The differential equations that behave that govern the behavior of linearity and non-linearity are linear and non-linear respectively. So that point we have just discussed in the last slide. So in most cases, linear models are adequate to explain the mechanical vibration. Okay, and one has to realize that in practice nothing is linear. Okay, there is no such thing as linear vibration. It is always an approximation. Alright, it is always an approximation, but most of the cases this approximation is sufficient to explain the vibration of the system uh, with enough amount of accuracy. You cannot define a completely, I mean, whatever equation you derive, and if you try to input that values, so suppose you get some equation of displacement x is as a function of time, and if you put the value of time and you find this value by using your equation, and then if you have suppose very what you say sophisticated instrumentation, and you are able to measure the displacement of time, displacement at that same instant of time. So suppose you measure this at after 2 seconds, and then you have some sort of a camera or a device that is going to measure the vibration, and if you measure this vibration at 2 seconds, in reality it will never be the same. This value from the equation and this value from the actual observation, it will never be the same. But you will find that in most cases the values obtained are more or less same, so they are in agreement. It is not like, you know, you will get this as 100 and this as 10. It will not be like that. So this might be 100.0001 depending upon the accuracy, and this might be 100.0002. Alright. So the difference is practically acceptable as far as application point of from the application point of view. Okay. Now, second thing, one more important aspect of a linear vibration is that the principle of superposition hold good. Okay. The principle of superposition hold good. What do you understand by principle of superposition? See, in the previous slide, we wrote this opposing forces as summation of spring force and damper. So we can add both these forces algebraically in case of linear vibration. This we cannot do in case of non-linear vibration. Okay, the principle of superposition states that for all linear system, the net response can be by two or more stimuli. In this is the sum of the response that would have been caused by each stimulus independently. Okay, and for a non-linear vibration, this cannot be done. Okay, so actual mechanical vibration are impossible to see. If you see the actual vibration, like for example, if you have a shaper machine which is operating on the shop floor, and if you see the, like if you have a if you attach some probes to it, and if you take the readings on the computer, then the vibrations which you actually get, that cannot be explained by any linear models. Okay, because in practice all the systems are going to behave non-linear. All right, I hope you are able to understand this explanation. All right, so it is slightly complicated, maybe you need to digest this a little bit.
Sir, can
So
you
this,
please explain the second point?
which one?
The
The
response caused by two or more stimuli is the sum of the responses.
So for suppose, see, a system has a spring. Okay, so when due to presence of spring, if the system is displayed, then the spring force is minus kx. Okay, and it also has a damper. Or suppose it has one more spring. Okay, so you have a one spring attached to a mass, and there is another spring attached to this, which is passing over this pulley or something like that. There is some kind of another mechanism. Let me just complicate this with more clarity. Suppose there is this mass and there is a spring attached to it, and there is a pulley system. I'll do it over here. There is a mass, there is a spring attached to it, and this thing passes over this pulley system. There's one more pulley over here, which is fixed at the center, and there's another pulley over here. All right. Now x1 is the displacement of this, and there is another spring attached to over here, and this is another mass, and this is m1, and this is m2. All right, and this is x2. All right. So now here you get two spring forces. Suppose this is k1 and this is k2. All right. So now this one spring force is minus k1 x1. Maybe plus. I am not going to analyze this whether it is positive or negative. Depends upon the direction of the motion. Okay, the spring force will be always negative. So suppose this is minus k1 x1, and in the second spring it is minus k2 x2. Now, if it is a linear vibration, I can add or subtract this, which I will not be able to do. Not possible for a non-linear vibration. I've just given this thing as an example. This is not the accurate solution of it. Just for your understanding, I have given this example. Is that clear now?
Yes, sir. Thank
you. All right. Okay. These are this ink. Any other question before I go to the next section? That is the vibration analysis procedure. Right, so we have seen the classification of vibration. Now let's go and try to understand how to analyze the vibration. Okay, so where are the various steps in the vibration? So this is an example, and this is an example. So in this you have a hammer. This is a hammer. So this is a block diagram, not actually actual representation of the process. So this is a hammering process, and this is the anvil. So basically there is some kind of base at the bottom, and then there is this elastic pad. So actually, whenever you're applying doing this vibration analysis, it may not be that exactly like a spring mass damper system. It can be in some other form. Okay, So these other elements also have elastic property, which also act like a spring. Okay, and then there is a foundation at the base. All right. So now I can convert this system for doing the analysis. I have to convert this into a mathematical model. Okay. So the mathematical model will comprise of what? A mass. It is the inertia element and a damper for dissipation of energy and is elastic element. So in this case, the elastic element is the soil stiffness. All right. Now here, this is a simplistic model. Okay. Or I can say this is a crude model. It is simple or a crude model. In which I have just clubbed the entire mass of the system into a single point mass, and I have just attached a damper and a spring to the system. Okay, but I can refine this model as shown in this second figure. Now this will have a single degree of freedom system, but when I refine this to in this form, this will be a 2 degree of freedom system, because each mass will have independent displacement. X1 and X2. So I am just this will be the anvil. So I am assuming that the elastic sheet also has some damping. This spring and damper is for the elastic sheet, elastic pad. I hope you are able to recall the figure. You have the notes with you, right? Elastic pad. So this is the damping of the elastic pad. And this is the stiffness of elastic pad. Okay, and then I can assume that there is another mass of foundation. Foundation also has some mass and it has some independent motion. So this is x1, this is x2, and the foundation is placed on the soil. So soil also acts as a spring. So you have damping provided by the soil plus the stiffness of the soil. Right? How to find this damping properties? How to find this stiffness? So you have to measure the various properties of the system to find those values. Okay, so thus you can convert a crude model into a refined model by by doing some thorough analysis. So what kind of analysis you want, that depends upon you. Like it depends upon what is desired from the what is desired in the form of solution. What is, so somebody comes to you for doing this analysis. So what is exactly expected from the engineer is what defines how the model should be refined, to what level the model should be refined. Okay, so so we have done this first step, that is creating a mathematical model. Right? After creating the mathematical model, you have to go for the next step. So step 2 is after you create the mathematical model, you have to connect this by using a equation, and that equation has to be derived by deriving a governing differential equation. So for GD stands for governing differential equation. So please remember the short forms. Okay. So this governing differential equation, some of the methods you have already studied, can be derived by using D'Alembert's principle. Or can be derived by using the principle of conservation of energy. there is Rayleigh's method. Right. So there are various methods by which you can derive this governing differential equation. Rayleigh's energy method. These are some of the methods which we'll be using. Then solve this governing differential equation. Okay, solve. How will you solve it? Using integration and by applying the boundary conditions. Right. So what are these boundary conditions? We'll see. What do you understand by boundary condition? We'll see it in a minute. Okay. And the final step is to interpret the results. Interpret. Right. So these are the various steps in vibration analysis procedure. All right. So what we'll do, we'll take an example of a spring mass system. So this is spring mass system, and here the mathematical model is already formed. It's a very simple model. So you have a there is no damping in it. Okay. So our first chapter is undamped vibration. So we are starting with the free undamped vibration. So there is no damper in it. Okay. So the amplitude of vibration will remain constant throughout the vibration. In theoretically, in practice, it will never happen. There will be some source of damping. It will be friction or any other thing that will decrease the amplitude of vibration. Okay. So for a given spring mass system, x is the displacement at any given point of time, x dot is velocity, and x double dot is the acceleration. Okay. So now we'll construct a free body diagram for this. So this is m mass with displacement x, x dot velocity, x double dot acceleration, and since the mass is moving on the right hand side, the spring force will act in the opposite side. Okay, so this is the spring force. Right, so first step is to draw the second part of the first step is to after creating the mathematical model, draw the free body diagram. Okay. Step 2 is deriving the governing differential equation. So again, I have the free body diagram, that is m with displacement x, x dot velocity, x double dot acceleration, spring force kx. Alright. So now we have to derive the governing differential equation, and we have stated three methods. So let's do a couple of them. So let's first do a D'Alembert's principle. So you should be familiar with this because you have done it already in the first year. All right. So can you give the statement of D'Alembert's principle? Or alternatively,
inertia force in the opposite direction of the motion.
Second law. Inertia force is equal to
inertia force in the opposite direction of the motion.
Yeah, but that is not the equation. The equation means you have to equate something with something.
Inertia force equals to opposing force.
Equal to opposing force is correct. All right. So let's write this equation. So total inertia force will be MA, and opposing forces will be summation of all the forces. Okay. And when you write this, you use a convention that all the forces in the direction of motion are to be taken as positive. In the opposite direction, they are taken as negative. Okay. So I will just rearrange these terms. So if I rearrange this equation can be written as summation F is equal to MA, and forces in the direction of motion is taken as negative. Okay. So what will be the summation of forces acting on this body? Summation of all the forces. What will be summation F?
Spring force.
Yeah. So can you tell me what should I write over here?
Minus kx.
Kx
Minus kx.
minus.
And A is mx double dot. So I can rearrange this term mx double dot plus kx is equal to 0. So this is our governing differential equation. All right. And you can derive this governing equation, differential equation by energy method also. So energy method, the equation is kinetic energy plus potential energy is constant. All right. So kinetic energy is what? Half mv square or half mx dot square plus half kx square is equal to c, constant. Now to derive the governing differential equation, differentiate this equation. Just differentiate with respect to time. So this equation becomes mx double dot plus kx is equal to 0, which is the same as our earlier form. Okay, so you can use any of this method, and we will be doing several examples using both the methods, and I will show that whatever might be the system, however complicated it might be, the governing differential equation will come same by using either of this method. Okay, so far what we have done, we have derived the governing differential equation. You constructed the free body diagram. The next step is to solving the governing differential equation. So I will quickly write the governing differential equation over here. So that is mx double dot plus kx is equal to 0. Okay. So now I have to solve this governing differential equation. Okay. So does anybody know how to solve this governing differential equation?
सर इंटीग्रेट करेंगे.
हाँ, integrate करेंगे या any other method you know? Okay, so the another method you can obviously integrate. See, if you when you try to integrate, you need to know the boundary condition basically. Okay, so if you just integrate this equation, you will get an equation with so many constants, but you need to find out those constants. No? So what I will do, I will just assume a solution. So this is the standard practice. So x is function of time, and I can write it as c into e raised to st. Okay, this is an assumed solution. It's an assumption. Okay, and substitute. So x dot will be c into s into e raised to st, and x double dot is equal to c into s square into e raised to st. All right. So substitute x and x double dot in the equation, and after substituting these values in the equation, what do I get is c into m into s square plus k into e raised to st is equal to 0. Okay, so the only possible solution is m into s square plus k is equal to 0, and that gives me the roots of this governing differential as s is equal to plus or minus I k by m. Okay, or I can write it as plus or minus I omega n, where omega n is nothing but your natural frequency, and that is equal to given as square root of k by m. Okay, so it is defined as the natural frequency, and that is numerically it is given as square root of k by m. All right. All right, so we are still on step 3, solving the governing differential equation. So now the roots, what are the roots of the governing differential equation? Roots of GDE are S1 is equal to plus I omega n, and S2 is equal to minus I omega n. Okay, so x is nothing but function of time, and the roots of governing differential equation have some characteristics. So let's list out those characteristics. So these roots are equal. Secondly, these are opposite. And they are complex. Okay, so when a governing differential equation solutions, roots of the governing differential equation solution has these characteristics, then the solution will be given as x into some constant c1 into e raised to plus, I'm just going to write this plus once, and then I'm going to forget about it. And c2 is equal to e raised to minus I omega nt. Right? So this is a solution. How do we get the solution? That is all part of the mathematics course. So I'm not going to go into detail into that. So if you are not able to recollect that, just remember this result. All right, because that then it will become an endless course. I'm already going into too much detail. So additional detail will be like unhealthy for this course, especially unhealthy for your health. All right. So now there is one more result I know, that is e raised to I theta. I can write it as cos theta plus or minus I sin theta. So sorry, e raised to plus or minus I theta is equal to cos theta plus or minus I sin theta. All right. So I am applying this result to this I into this coefficient and I into this coefficient minus omega n. All right. So when I expand this, when I apply this and expand this, I will get x in the form of a1 cos omega nt plus a2 sin omega nt. All right. Now I have to find. So I hope everybody has understood how I got this. I have not expanded this equation. Anybody who has not followed this, how I got from here. So from 1, I have come to 2. Can I continue?
Yes, sir.
Yes, sir.
So now what I need to do is I need to find out this A1 and A2, right? So to find out A1 and A2, what I need is we have to apply. So there are two unknowns. So we need two boundary conditions to solve this equation. So first boundary condition is that at t is equal to 0, the initial displacement is x is equal to x0. All right. So substitute t is equal to 0 in this equation and x is equal to x0. So I get A1 equal to x0. All right. So substitute a1 equal to 0, x0 in this equation. So x is equal to x0 cos omega nt plus a2 sin omega nt. All right. Now again I have a2 is still remaining, so I will again have to apply some other boundary condition to find out a2. So I am going to put the second boundary condition, and that is at t is equal to 0, the velocity x0, velocity x dot is x0 dot. That is, this is defined as the initial velocity. So I am, if you see, I am not imposing any specific what you say boundary condition. These are in very general terms. Okay, so to be precise, generally the problems are that initial velocity is 0, initial displacement is also 0. All right. So so now I have to find out a2. So what I need to do first, I will differentiate the equation of x. Okay. So this will become x0 dot and substitute x dot is equal to x0 dot. So this will become minus a1 omega n sin omega nt plus a2 omega n cos omega nt. Is that comfortable? All right. I have just taken the derivative of this equation. So x dot I have taken. So that is x0. Derivative of cos omega nt will be minus sin omega nt into omega n. So omega n into sin omega nt plus a2 omega n into cos omega nt. All right, and then substitute t is equal to 0. So first term becomes 0 and this cos of 0 becomes 1. So and x dot is to be substituted as x0 dot. So what do I get now? So again I will do it over. So that is what I have done over here, and just substitute t is equal to 0. So first term becomes 0 and this term becomes this when t is 0, cos term becomes 1. So I get x0 dot is equal to a2 into omega n, or a2 is equal to x0 dot by omega n. Alright. So now my final equation, I have got both a1 and a2 is x0 cos omega n t plus x0 dot by omega n sine omega n t. Alright, so this is my final solution. Okay, so we have derived the governing and we have found the solution also. And so what you can see from this, what can you conclude? Can somebody tell me? Last step is interpretation of result. Interpretation. So all the remaining steps I have done. So interpretation is remaining. So based on this equation, what can you interpret?
It is linear.
It is linear. So that is already we are explaining. See, if it was not linear, we would not be able to solve this. Because it is linear, we are solving this. I am asking based on the equation of displacement, what is the conclusion that you can derive?
It is oscillating.
Oscillating, correct? And how? What is the nature of oscillation? There are these two components to it, or two terms. I can say there are two components, and one component is a cosine component and second component is a sine component. So both these sine and cosine components are getting superimposed. So you will get a result which is like a sinusoidal or a cosine wave. All right. So the response of this system will be like a sinusoidal or a cosine wave. I should not make it 0. It will be very specific. Just the result that I will get, I will be something like this. That is on y-axis there is displacement, on x-axis there is time. All right. So this is how I am expecting to see the response of the system with time. Is that clear? Okay, now go ahead and complete the small part of the quiz that was left yesterday. I will just open the quiz.
So in case equations are non-linear, so they cannot be analyzed at all.
No, you cannot analyze. No, see, if it is non-linear, then there is you cannot establish any sort of what you say. You cannot see if you are going in a circle. I can say that you are going in a circle. Okay. All right. And the equation of that circle is x square plus y square is equal to r square. But now if you are going in a zigzag mode, right?
Mm-hmm.
Right. So how can I define the motion? I can just
Okay,
say it is a zigzag. You are going in a zigzag mode, but I cannot define, right, in terms of the variable that x square plus y square is equal to something, or x raised to n, ax raised to n. I cannot write any equation which will define the motion.
yes, sir.
What the idea? That is the
Yes, sir.
interpretation of the. Okay, I have opened the response. Open the quiz link. Any quiz link has been already sent to you on your group, and submit it, and that's all for today. There are 5 minutes remaining. You can complete the quiz. If you have any more questions, you can definitely ask.
Sir,
Yes.
sir, can you again explain the getting of GD from energy method?
Pardon?
Sir, can you explain the derivation of GD from energy method?
Energy method. See, the energy method, the equation, it says that the total energy of the system remains constant. So kinetic energy plus potential energy is constant. So kinetic energy is half mv square, that is half mx square, and potential energy of the spring is half kx square. This total of this is constant. And then you differentiate this equation. So mx square, half mx square becomes, okay, I'll just write it. So this becomes, once I differentiate, this differentiate, after I differentiate this equation, this becomes half into 2 x dot x double dot plus half 2 k x into x dot. Okay, so half cancels, x dot cancels everywhere, and this is equal to 0. So what remains is mx double dot and kx. So that is what I've written over here.
Okay, sir, yes, understood. Thank you.
Sir,
Yes.
derive GD by 3 methods. So you
Third
taught us
method I have
DL.
not, energy method I have not incorporated, because basically what it says is that maximum kinetic energy is equal to maximum potential energy. So I have not included that in this discussion. That will do it for multi-degree of freedom system, you know, when we solve this. So in that case we'll do. For your single degree of freedom system, these two methods will be sufficient, because that method is not that easy to apply. So unless it is a really complex problem like a multi-degree of freedom system, I would rather not suggest applying that. Then in between you have a 2 degree of freedom system where there will be another method, Lagrange's method. So that is slightly complicated. We'll see all these methods. So I am giving you methods which are appropriate for that section. Okay. Okay. All right. I think time is up. So let me just publish the answers. All right. So scores are posted. You can just have a look at your answers. All right. That's all for today. Thank you.
Thank you, sir.
You can go to the next lecture.
Thank you, sir.
Thank you, sir.
All right.
Thank you, sir.
All right. Thank you.